title of his lecture is Degradation and Stability of Perovskite Photovoltaics, Indoor versus Outdoor Studies. So Eugene, floor is yours.
Thank you, Pavel. Can you hear me?
Yes, perfect.
And can you, one second, I'm trying to do it in presentation. Yeah. Can you see my slides?
Yes.
Okay.
Just hold
Yes,
on.
first of all, thanks organizing committee for giving me an opportunity to talk on Zoom, and especially for Professor Troshin for his persistence in science and scientific communications. Yes, I'm from Israel, from the Southern University of Israel, which is called Ben Gurion University of the Negev. And I ever introduced that the Negev is a desert which occupies 60% of the area of this small country. And you can see our campus and you can feel that it's really in the desert. And our campus is the place of faculty, which is called Jacob Blaustein Institutes for Desert Research, and it consists of three different institutes, which aim is to develop technologies and to do fundamental science to develop these technologies in order to survive in the desert. The one institute, the biggest one, is the agriculture and biochemistry and around. Another institute, the Institute of Water, there is some more complicated name, but it is. And you know that one of the main problems historically in Israel was an absence of sweet water because we have only one source of it, it's the Lake Kinneret. But now it's all in the past. 80% of our water is desalinated water from the sea. And the technology, reverse osmosis, was mostly developed in the Ben Gurion University. And our institute is called Institute of Energy and Environment, and we are inside this institute in the Ben Gurion National Solar Energy Center. And yeah, we have very good son, and Pavel knows very well, and also some of his students. So we have a noon time, plus minus 2 3 hours. We have a global spectrum very near to AMS 1.5 standard spectrum, and we also have a very high ratio between direct and diffuse light, and you know that physics forbids to concentrate geometrically diffuse light, sunlight, but we can do it because we have a lot of direct sunlight, and I will talk about it. You can see, for example, last year it was published a path for perovskite PV commercialization as a perspective from the United States Solar Energy Technological Office, and you can see this and not a usual triangle, but more complicated geometry. And what we need among other stuff is accelerated life test protocols and field validation of them. The field validation means outdoor testing, and this I will talk about it. I will talk about both points. What's the problem with outdoor testing of perovskite solar cells? First of all, in all PV technologies, a measurement outdoor is complicated. Why? Because every moment you have different light intensity, different light spectrum, different angle of incoming sunlight, and different temperature, because the environment temperature also changing during the day, and another, the cell temperature strongly depend on incident light power. This will be for silicon cells, for gallium arsenide, for anything. In addition to this, the main problem with perovskite outdoor analysis is not that there is a degradation. This is okay, long-term degradation. The main problem is that in addition to this, and most of this audience probably knows about it, is there are slow transient processes, so-called, and the degradation in in perovskite PV can be reversible and also bias dependent, means that dependent on electrical biases. And then I will show you some examples of it. And I like this paper, is a pretty old paper, already 6 years ago, came from Lozana Group, showing that they measured indoor and the solar simulator, but they show that the degradation of their perovskite solar cell was completely reversible. What does it mean? That it is some degradation under light, and then in the dark, it's restored by 100%. The second cycle of light started with 100% of initial degradation. And you see on the right of this figure, you see that the four cycles, only 100% was restored in the dark. Then the group from China showed they were first, but then it was confirmed by many groups from many perovskite cells. Opposite behavior. They call it fatigue behavior. And what does it mean, this behavior? That the cells degraded in the dark and restored under light. Very long light sorting effect, and many of you know that the light sorting exists almost in all perovskite cells. What we show in our joint papers with many different groups, we show that these two processes, these two degradation pathways, can exist, can be observed for the same devices. In that case, it was devices produced by Yulia Gallagher group, and depending on stage of the device degradation. I will show you. So if you look, and this also, the paper was the first attempt to compare degradation indoor and outdoor. Indoor, it was a very fast degradation, and remember, 2016, and T80 is 1 hour. Maybe, I don't know if previous speakers introduced these parameters, the figure of merit of degradation is time, we call it T80, at which initial efficiency degraded by 20%. T80. 1 hour in this case under continuous illumination of one sun at room temperature, solar simulation. Then, if you take it something like 1 day and compare it to 1 day degradation outdoor, you will get similar. Okay, in outdoor, the outdoor was in Slovakia, and it was a very strong light intensity, almost 100, almost one sun, but it's not one sun exactly, so it's a bit less. But then the difference started when nighttime introduced. In the outdoor experiment, there is a day and night, yes? And then we can see that if you measure it during different days, during 11 days of this experiment, it was degradation in the day, during the day, and restoration at night. After, and we call it behavior one. I will use this term in my talk. Behavior one is classical degradation under light, restoration in the dark. But after 11 days, I will show it in more details, it was opposite. We call it behavior two, degradation at night and in the dark, and restoration under the light during the day. Another observation you can find that in this case it was not completely reversible degradation. Yes, at least it should be some combination of reversible and non-reversible mechanisms, and maybe something more problematic I will show you in next slides. But in any case, the idea of T80 doesn't exist, doesn't help anymore. Every day you have your own T80. So what you can do? You can, for example, think about only first points, and then you will have, we call it T80 maximum. But in this case, it's misleading because we could not introduce the degradation during the day, because what we are interested in integral in energy generation during uh, this operation, outdoor operation. What we suggested, and the paper was called the new figure of merit for degradation study, we suggested to take it as a figure of merit, not efficiency, but energy output during a day. The production of energy during one day, and T prime 80, it will be degradation time during which this day energy output degraded by 20%. And this will be independent on a type of reversibility, independent of its reversible or non-reversible. It can be a nice figure of merit. But we also advocate that we need to look during outdoor study, we need to look on the parameter which we call performance. The performance means that in integral of energy generated during one day divided by integral of power of sunlight, incoming sunlight during the day. So it will be energy to energy, and yeah, power dt. And one day will be 1 point. I will show it later. Actually, you see it on this graph already. Yes, this again, what you show, the change of behavior 1 to behavior 2 at some point of degradation. Then we decided that we need to study more in detail the restoration processes. And this experiment was done under solar simulator indoor, and we decided to stop illumination at different degradation stages. The figure A show you we illuminate the cell until TAT, until efficiency dropped by 20%, and then switch off the light. And then you see very fast and completely reversible degradation. In figure B, we allow the efficiency degraded on 60% of its initial value. And again, we see restoration in the dark, but this restoration is very long. It's more than 50 hours. What does it mean? It means that in outdoor experiment, you will see this degradation as non-reversible. It's a reversible degradation. We call it quasi-reversible. But in the outdoor experiment, you will see it as non-reversible. But most interesting point was when we allow efficiency drop in 50%, and then we see when we switch on the light, we see decrease, very strong decrease in efficiency by different ways, by different patterns, but it was reproducible because we didn't believe in this result. We reproduce and reproduce and reproduce, and then we think, maybe this corresponds to this change in behavior 1 and behavior 2. We call this, we call this behavior drop in the dark. What I need to say is that for that time we were not very educated, and first of all, we did all experiments, all aging in open circuit. How this experiment was done for outdoor and indoor. For outdoor, we just put the cell and measure in open circuit and measure it, then go to the lab, and 3 times a day we measure in the morning, in the noontime, and in the evening on the solar simulator. This experiment, indoor experiment, was also done after aging the cell under the solar simulator in open circuit. Now we understand that it can be different. And first of all, we don't need to do this experiment. We really advocate for measurement only in maximum power point, and I will talk about it later. Yeah, we speculate about different mechanisms what it can be for reversible, irreversible, and apparently irreversible degradation. What we know for sure is that In this particular experiment, it was no perovskite decomposition and phase segregation because we measure carefully on the degraded samples. We measure Raman spectroscopy and PL, and it's either ion migration or bulk transformation. And of course, it can be also degradation of interface degradation and hole and electron conductive layer. I really appreciate the paper published 2 years after by also Lausanne group. Konrad Damansky was the first co-author. They measure on a big statistic. Yeah, it's a problem, but we now understand that if you really want to do perovskite stability study, you must have big statistic. And then on a big statistic, they show that if you age the perovskite cells in open circuit, short circuit, and MPP, you get different results. And now there is more or less agreement in the community that the most strong, most fast degradation is in the open circuit. But what is strange that a priori we may think that MPP conditions, yeah, I didn't say MPP, it's maximum power point condition, should be something between short circuit and open circuit, but it's not. This curve, if you drop, you can see it here. We wrote and published some short review about these effects, not only perovskite, but in many other solar cells technologies. You see that we put efficiency drop, efficiency degradation, and as a function of electrical bias, and you see that it's not monotonic curve is maximum, and MPP is maximum, it's more stable. At least I can explain it only by one way, that you have at least two different mechanisms of degradation which dominate in short circuit and open circuit, and one mechanism is decreased with maximum electric field, with increasing electrical bias, and other mechanism with decreasing it. That's why you have maximum somewhere between. Yes, what kind of this degradation mechanism can be in short circuit where it's a maximum electrical field inside, it can be intrinsic and extrinsic ion migrations. In open circuit, it can be extrinsic ion migration as well. But most important, there is a charge carrier accumulation and defect formation because we generate electron hole pairs and all of them should recombine. There is some accumulation of charge, and chemistry and trap generation really like these conditions. Yes, I told you that in the first experiments we didn't appreciate the effect of electrical bias. Here, 2 years ago, we published another paper with the same group of co-authors, August, and we repeat this experiment with open circuit aging and short circuit aging, and you can see that in open circuit we reproduce our results for so-called deep in the dark, but when we age the cell in short circuit, this is open circuit, and then for short circuit, not. We just show conventional restoration of efficiency after switching the light off. This is very interesting. Another interesting point in that paper, in this experiment, that we also apply negative electric field for a short time, it's 0.5 volts negative electric field, and we show that we can affect restoration. Indeed, this is very interesting and can be used in the future in some, let's say, smart electronics during night. But what we also formulate in that paper that research strategies towards improvement of operational stabilities for the PV material and devices exhibiting at least partially reversible degradation may include both mitigation of the degradation mechanism and second, promotion of the recovery processes. Most of published study today on perovskite PV were aimed to the former strategies. One, mitigation of the degradation mechanism. Knowledge about attempts to promote the recovery of perovskite PV is rather absent and limited, and such kind of electrical therapy is possible, I think, and necessary to be developed. Yeah, now we coming back a long time. In 2011, Frederick Krebs initiated collaboration. It was the time when OPV was studied, and we understood that there is no standards for study stability and degradation, and it was an idea. Let's suggest our own academic standards. Another problem for that time that everyone used whatever they want. Light sources, it was really big mess in the publishing date. And this was published in Solar Engine Materials in Solar Cells. I was in my process for that time, and we call it ISIS protocols. Why ISIS protocols? Because the first discussion of these protocols was in the conference which called ISIS and was previously conference on stability and degradation of organic photovoltaics, now organic and perovskite photovoltaics. And it was five groups of these protocols. It was very successful, and really people use these names and these definitions, and it really helped to make some orders. And then in 2020, Monica Lirucanto and myself, we initiated collaboration to suggest basis of these ISIS protocols, but to add something which is specific for perovskite solar cells. Or what is specific is light reversibility of the degradation and bias dependence on degradation. And we suggested to add two groups of these protocols. One is for light cycling in the lab, and another one for study of biostability. What I would like to say is that it was really very hot discussions to come to consensus, and eventually we did come to consensus, and I'm very happy about it. So, one simple question: how not only how to measure, but how to report? What is T80, for example? Most of you, if you sometimes study degradation of perovskite solar cell, you maybe see the second, the lower graph rather than classical first graph. What is T80? Even not complicated as I showed you before, but even under the continuous elimination. Yeah. Almost the same time, the AMI group published a short paper about also necessity to introduce light dye cycling in the dark in a way just light dye cycling and also maybe with temperature. Last year, Chinese group published it's something between review and analysis paper in Nature Communication, and they study devices. First of all, they advocate and really like this using big data methods for stability analysis of perovskite solar cells, and they use this called perovskite stability database. You can see the reference in Nature Energy 2021, and you in this graph shows the number of protocols reported as a function of the protocol. And you see that until today, the most stability study is just measurement in the dark on a shell. ISIS L1, there is another maximum, but you see that all outdoor studies and light cycling studies are very, very small. It's almost absent. Okay? But we should start doing it, and we'll do it. We are in a community, not only our group. I will show you what is the problem with outdoor studies. This is our recent results for our own cells, and you can see that this is efficiency as a function of imbalance during the day. And you can see there is a degradation, and in a fresh cell, they show behavior number one, degradation during day, but when the cell degraded, it changes to behavior number two. You can see it. No, I'm sorry. Really sorry. This is indoor study. It's protocol LC1. light diode cycling under one sun and room temperature. And this is very consistent. Behavior number one changes to behavior number two. When we start to see it outdoor on the same times, and you will see a number of slides about it, but not to be big mess, you can see that it's not the case. It can be behavior one, it can be behavior two, but it changes again. And then if you really look at it, if we calculated performance factor, you can see that there is no monotonic decrease in performance factor. There is a period when it starts to increase, and there is some correlation between light intensity. This was a very unusual weather in June in the Bakir, in the desert, that was raining. And the cycle, the periods when the intensity of sunlight was so very small, it's also present. So we really need to understand it. Still, we are far from understanding. Now about accelerated stability studies using concentrated sunlight. I studied it a long time ago. I showed you our first experiments for OPV, and then I stopped it when we start to do perovskites. Why? Because we really need a high statistic for perovskite. And our system does not provide, we can do one experiment with one sample. But now I'm more optimistic about it, and I think we really need to do it, and I will explain you why I think so, and I will also explain you very optimistic results using our idea by different groups. So this was the first experiment, 2010, in collaboration with PCHT PCBM OPV, produced by Frederick Krebs Group, and this was our system for that time. You can see it, it's a concentrator, a small parabolic mirror, staying outdoor in a balcony now, and it's actually this system is 20 years in the operation. And it concentrates sunlight on a flat mirror, then redirect it to optical fiber, and then come to the cell, which sit out indoor. And we also sit indoor. And if the cell area is larger than the diameter of the fiber is 1 millimeter, and we can get up to 10,000 cells. But if we need a study, for example, 1 square centimeter cell, like in this case, we put a homogenizer, it's nothing else as quartz kaleidoscope, and of course, intensity drops immediately from 10,000 to 100,000, but it's not. So what you can see that this is it was non-encapsulated sample, one sun outdoor, temperature was 50 C, temperature of the cell. It's our usual temperature. If environment temperature is 30, 35. A very small degradation in short-circuit current in VOC, but if you put it on 60 suns with almost the same temperature, you really ruin the cell. You have 2 times degradation in short-circuit current, even more in VOC, and fill factor go to its minimum value, 25%. But what we do, we start to cool, and we see if the experiment under 30 degrees centigrade, there is a degradation, but not so strong. Yeah, you see. Still more or less nice fill factor and small degradation in short-circuit current, and we'll see. And for that time, we were very optimistic about it. This is very interesting results, which will be more important for me for later discussion. This we do for already for perovskite solar cells, and you see we age the cells with this system under 10 suns, 20 suns, and 30 suns, but under 2 different bias conditions, in open circuit and short circuit. And you see that for open circuit, the mechanism of degradation is so that if we plot it everything as a function of dose, not an experimental time, what does it mean? Dose, it's sun hours. If light-induced degradation is linearly proportional to light intensity, the degradation under and dose under 100 hours at one sun should be the same like degradation in 100 suns 1 hour. And you see the case. And this is the case when we may say, yes, this is a degradation mechanism which can be studied. And you can find acceleration factor, and you can study by this acceleration regime, and then you can predict what it can be for standard regime. Immediately, it's not the case when you age the cell under short circuit. You see that it's anyway, you put it under sun outlet, but it shows 3 different experimental curves. And what does it mean? That there is some other parameter, other mechanism, which not only rate of degradation is not only proportional to light intensity. If it's short circuit, yes, what it can be. It can be, for example, ion movement and the temperature is involved. If the temperature is not the same, then you can explain these results. But in my context, what is important? These particular conditions could not be used, and this particular degradation mechanism cannot be studied with acceleration regime. Why? Because you introduced something else. I will talk about it later. Yeah, then we start to use another system which has no fibers. It's a flat mirror with state outside and directs the sun, redirect light to, one second, I show you again. Redirect light to the another flat mirror, then parabolic mirror, and then we can use chirping of the sunlight, and with this chirping we show that until 100 of suns we have no increasing of temperature. This results was in the method for perovskite fields encapsulated between two glasses, and thermocouple was introduced in the encapsulated cell. Recently, with a group from Princeton, Quinn Birmingham and Professor Lin Lu, we submitted, and it's just accepted, a short paper, which is called Accelerated Aging of Organic and Perovskite Photovoltaics to Nature Energy, in where we not only suggest the importance of this high light intensity and high temperature and other high acceleration factor degradation regimes, but we also discuss and concept of accelerated factors, and we discuss where we can use it and when we could not use it to predict their real-world operational lifetimes. This is a graph which is a computer simulated graph, but it's very similar what you see in my experimental results with accelerated concentrated sunlight, but I will explain you what it is. A is computer-generated pseudo data comparing solar cell performance evolution under reference and accelerated agent conditions for duration t-test. Yes? Degradation range for each curve were used to calculate the acceleration factors. The acceleration factor definition is the degradation rate at the accelerated conditions divided by the rate to the rate at reference conditions. Yes? And these acceleration factors indicated near to every curve. B. The data in plotted on a unified equivalent time to the reference condition by multiplying the aging time by accelerated factor at each condition. In my previous experiments, which I show you in this one, this was just product of light intensity, light intensity and I'm sorry, I did something wrong. Yes, light intensity and time. Yeah. But I will explain it in more. Yeah. Then if you use this equivalent time as the reference condition, you can see if all of your points sit it on the same curve. If it is, you are in. you are really, you have a one mechanism or maybe number of mechanisms which show constant acceleration ratios, and you can use it then to predict it for in operational condition and standard condition. But it can be different, and I show you these results also. This is number C. Even for equivalent time, it doesn't sit it on accelerate on the same curve. Yeah, I'll just tell this because it's very important, at least in my mind now. I'll explain you again. For data like those in Fig 1 that exhibit a consistent functional form with increasing stress, an accelerated factor AF can be defined for each stress level by dividing the degradation rate of solar cells aging at each accelerated conditions by the rate of those aging to the reference conditions. Typically 2550 C or 1 sun or outdoor use. This may be more complicated because it can be very seasonally and geographically. In practice, accelerated factor indicates how much faster a solar cell is aging at a certain elevated stress condition. For example, 10 times faster for accelerated factor equal to 10. But what it can be stress conditions? It can be light intensity, temperature, humidity, electric field. Data in Figure 1a can be fitted to exponential decay functions to extract degradation rates and calculate acceleration factors shown above each curve. Using the calculated acceleration factors, the data from different stress conditions can be plotted onto a unified equivalent in time as a reference condition axis, as shown is Fig 1b, where all data collapse on a single unified curve. And this is a case of effective accelerated test. Since the data in Fig 1c do not have the same shape, accelerating factors cannot be extracted. In 2011, Highland and Courses published in Solar Energy Materials and Solar Cells that proposed that the ratio of degradation rates with thermally activated, means arrhenius, or light activated, means first order photoinduced, can be expressed by this formula, and in a number of papers successfully shown that it can be, and I really want to show you these papers. Very interesting work. They do it mostly on 4PVs, and now they also move to perovskite. Is a group of Christoph Brabeck, which do accelerated aging with real stabilized temperature and high light intensities under simulated sunlight up to 300 suns, and very important then for many, many cells in the same experiments. And you see that just extract for the abstract, we demonstrate that the temperature kinetics of P3HT PCBM was found to be Arrhenius governed with an activated energy of 27 kilojoule mole under continuous eliminations up to 300 suns equivalents. Finally, it was shown that the velocity of light-induced degradation of short-circuit current depends linearly on the irradiance dose, light intensity, at a given temperature, starting from normal illumination conditions up to at least 300 suns. This makes high light intensity, high temperature very successful, powerful for swift screening of the lifetime of novel and film solar cells and materials. And a very recent paper from my co-authors in this short paper in Nature Energy, Green Burlingame and Professor Lin Lu from Princeton, and they study all inorganic solar cells with 2D caps, and they show, I will read, device with 2D capping layer did not degrade at 35 C and required more than 2,100 hours at 110 C under constant illuminations, and to degrade by 20% of their initial efficiency. And degradation acceleration factors based on observed Arrhenius temperature, I will show you the results, allow to predict intrinsic lifetime of about more than 50,000 hours. Of course, when we let me show you, when we want to use this this formula, you have one exceptions, then can be wrong. That two different mechanisms are independent, light induced and temperature induced. And then under outdoor, we can see maybe it's not ever the case, but we really need to do these experiments more and more. And you see their results, I mean the Bristol results. You see the in the upper curve is the experimental results of degradation. Unkept cells degraded even in 35 degrees at 1,000, and there is no any degradation for kept cells, and it start to be degraded with high temperature. And when they plotted with this equivalent time at 35 degrees using accelerating factors, you see that a beautiful one curve, and it means that it can be considered as a good example of accelerated test. So I think I should finish and take home messages. I will be very short. Outdoor diurnal changes in outdoor performance as a result of combinations of three different effects. Diurnal changes in intensity, spectrum, and incident angle of sunlight and cell temperature. These observed for any kind of source, not only for perovskite. For perovskite is a transient, in addition to this, transient process instabilities in perovskite solar cells and see long-term degradation. Second, suggested figure of merit is performance ratio and the time of 20% of withdrawal. We really suggest for outdoor study protocol ISOS 03 at maximum power point, and also don't suggest to do any UV filtering. For some groups do it, I think it's wrong. More research needed for indoor accelerated tests to validate outdoor stability and predict operational lifetime with analysis of accelerating factors, and to develop a set of tests each based on one stress factor and analyze the results, individual acceleration factors, using big data methodology. For this, we really need to have big data. And also need for round-robin outdoor stability experiments over the world. And my acknowledgement for all my co-authors from our university, Professor Visoli Fischer, and our students, joint students, and from HDB Berlin, University of Southern Denmark, and Barcelona, and some thanks for support from Europe and from Israel, and thank you very much for your attention.
Thank you very much, Eugene, for a very nice lecture and being perfectly on time. So it's open for discussion.
Professor Katz, do you hear me?
Yeah.
Yeah, this is Alexei Tarasov from Moscow State University. Thank you very much. Amazing talk. I have a question. Do you think it's important to settle some standard parameters of MPPT process regarding, for example, the velocity of voltage change, their precise time diapasons for their solar cell performance stabilization before the next step of MPPT process and so on? Because what we learned in our laboratory, we have our in-lab device for MPPT testing, and we experienced a lot of different results when we so used to measure it correctly. Particularly, we found that it's very important to adjust right parameters of MPPT tracking. And I feel that many laboratories in the world are using different setups and consequently different protocols for that. So how to compare this data correctly, in your opinion? Thank you.
Yes, you are certainly right. And this is a really very good question and real problem. So you're really right. And it's a problem even before MPPT tracking. How to measure, for example, efficiency? How to measure efficacy? How to measure efficiency? What do you need? Do you have a standard to make a light socket?
I
Yeah,
feel
most of what? Huh?
I feel that the most correct way to measure IV curve is quasi steady state. However, it's rather long, and you might be in danger of overlight socket,
Yeah,
let's
yeah,
say,
yeah, I agree,
or
but
over voltage load.
yeah, but this is again, you talk about MPPT. You put MPPT in time and see. This is what the community accept now. It was a time ago. I think it was almost the same time we wanted to make our consensus about aging protocols. It was a paper published about this kind of academical standards for measurement of IV curves efficiency. And still, it was a lot of discussions. They couldn't come to same. When you do MPPT, you are certainly right. Yeah, and also how you measure IV curve. What is this? All these times and the rate of change in voltage. It's tricky. And also, I didn't mention, but we all know about this. Hysteresis makes it the same with MPPT. But the problem that you you may do it in your way, but for example, I come to this problem when wanted to establish this outdoor ISOS comparison all over the world. And of course, everyone has its own MPPT tracker, but there is big groups. There are groups which use some MPPT produced in uh, in Yugoslavia, in Ljubljana University. There is MPPT which sailed by Friedrich Krebs and from Italy, and also a lot of MPPT trackers produced in Holland. We decided for the first time not to allow everything. Everyone who say you have your MPPT can do it. And in this case, our aim is to compare effects of different climates with a huge difference in climates. For example, we have a Hong Kong and the desert in Israel. But at the same time, this question come, and we need to do it. And I think that it should be, and there are some papers published about it. First, in one laboratory, you have your own MPPT, you know what you do, you change the parameters, and you see what is different. But the question is to 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 you should compare it with something. And of course, what we usually do, we go to the lab and measure IV under solar simulator. But again, it's very strongly depends when you do it, in which stage. In the middle of the day, when the cell is light soaking, or in the evening, when it's already seated sometime in the dark. Our MPPT also allow us to stop and to measure IV, for example, every hour or every 3 hours. And again, it's a big question. What if this IV measurement also affects something? So we really need to think about it and to collect more data about it. Yes, this is one of the big problem, and you are right. Not only in also indoor and outdoor. Yeah, but we educated during a couple of years very much, so we will understand it,
Okay.
and maybe we come to some standard suggestions. Yes.
I suggest to give a chance someone else to ask a question.
I'm sorry for long answer, but this is really a very clever question.
So thank you, Professor. Very impressive presentation. So I'm Zhong Haoliu from Huaitong University of Science and Technology in China. So I have some questions about the outdoor stability and the indoor stability. So I noticed that you have conducted the stability and the high intensity illumination. So my first question is how to translate. How to translate the high intensity aging to the practical. Lifetime of perovskite cells. This is the first question. And the second question, I noticed that some stability in your presentation is about NIP structure of perovskite cells. So actual perovskite cells may be with different architectures. Currently, maybe PIN sometimes have been recognized to have better stability. So how to distinguish the difference between the stability of perovskites with different architecture? So this is the second question. The third question is about the scalability. Just how maybe would you please give some advice for the future practical application of solar modules? I mean, how to evaluate the safety of perovskite solar modules? Is it different from small area size? Okay, that's my question. Thank you.
Thank you very much. Yeah, I need to give another lecture, but some lecture I already gave. So let's talk about the second one. There is no any way to measure stability and degradation of all architectures. It can be different, and the mechanism can be different. That's no question. About your first question, I show you this how to do it. For example, look on this slide. Yes, look on the right slide. It's measured under, agent was in short circuit, and it was under 10 cents, 20 cents, and 30 cents. Yes? So, when we plot it as a function of dose, you mean that we believe that the degradation is linearly dependent to light intensity, then you see that it is the case. And in this case, you can simply calculate acceleration factor, you can trust it, and you can predict what it can be at one time. And it was done in these two papers I mentioned on a high statistics. The one is a paper from Christoph Bradrick for PV, and another one from the paper from Princeton. About modules, I think as a guy who spent his life on measurements of solar cells, for me is very interested to measure two terminal modules on two terminal tandem cells, silicon perovskite, because it can be completely different temperature dependencies, spectrum dependencies, or whatever. It can be different mechanisms. Frankly speaking, I'm just starting. We now have a project which we need to measure mini modules. It's not a modules, mini modules on 4-terminal silicon perovskite solar cells made in IMEC. And I will see if some technological procedures which used to change solar cells to solar modules introduce some additional degradation mechanism. Difficult to say a priori.
Okay,
I
probably.
don't know if I answered your third question.
Okay, probably one more question from the audience. Okay, then I would like to ask one question about these acceleration factors. So, for instance, this slide is very good. For example, so these guys, for instance, they introduce acceleration factors based on the observed Arrhenius temperature dependence. That's like they got from your slides. So I'm still curious. I mean, if we operate solar cell is exposed to like a combination of several stress factors. And if we like skip atmospheric ones like oxygen and moisture, which could kill the device at any moment, and it will not be, let's say, in any model, I think, then we have light, temperature, and also electric bias. And all these accelerated tests, they suggest that we like skip all the factors except one. Let's increase the temperature, or let's increase the incidence light intensity, and see what happens to the device. But to my opinion, this could, I mean, as far as I understand the problem, this could work only to some degree of accuracy, only if we, let's say, select the major stress factor, like probably light for perovskite solar cells, and then we, let's say, have certain error which is like introduced by other stress factors which we do not scale up proportionally to the, let's say, light intensity. In that sense, I'm still wondering how one could extract any reliable data for a solar cell, just for instance by increasing the temperature following the Arrhenius temperature dependencies. So could you please comment on this?
Yes, yeah, first of all, I agree with you. Actually, as I understand you, it's not a question, it's a comment, and I will comment on your comment. You're right, surely you're right. Only my correction to you is that, for example, in this particular experiment, they don't exclude different factors. A light intensity one sun is still in the experiment. it was an encapsulated sample, they say in air, not outdoor, but in air. But they really change only one parameter. And you're certainly right that to use these acceleration factors for predictions, to say that they will stay 50,000 hours, it's a very tricky, because we know, and we know, for example, in our lab we show it, that, for example, light and temperature, they are not independent. When you combine increasing light and temperature, there is something more effectively degrading factor. And the same, I'm sure, will be with humidity or whatever. Yeah, and you can use, I would use this number very accurately, but not everybody. To suggest to think as a upper level, for example. And what we can use this experiment, and we should use, I really advocate for this, to screen new materials, new architectures. For example, it was a question about pin and nip structures or something else. But you're right, we should be very careful about it. In the beginning, we should understand the mechanism and check, as I said, that they are seated on the same curve after analysis, and only after that. But I would like to say that when we do any indoor tests for perovskite, they are already accelerated. Not high accelerated factors, but if you do continuous illumination, it's for sure accelerated comparing with outdoor study. Even if you do light cycling under one sun, it's accelerated, because outdoor, in many cases, it will be not one sun. So the idea of acceleration factor analysis of it, an idea to separate mechanisms dependent of different stresses, this is one way to analyze outdoor data. What is the other ways? The other way is to compare outdoor and some modeling, and there is papers about it. I didn't mention it because of time. It's a paper from Ljubljana group. They measured indoor temperature coefficient, light intensity coefficients, spectrum factors, then model what it should be during the day, and then comparing with experimental, they extract degradation or long-term instabilities. And the third way is to compare outdoor versus outdoor in different places. But anyway, it's a very long and difficult way. And what the previous question was asked, okay, what about the electrical effect by MPP tracking? There is also, so it's a very long way.
Okay, Eugene, there is one more question. We are, let's say, behind the schedule, but since we have no chance to communicate with you during the lunch break or coffee break, I suggest we stay a few minutes more, and I'm giving the microphone to Professor Parashuk.
Женя, привет, Паращук. My question is about, thank you very much for this story. The problem is extremely complicated. And you know, now people ask artificial intelligence to help in this very complicated problem. What is your view? What do you think it will be useful to use artificial intelligence to analyze this big data? Or we need to think, first of all, by our minds?
I will start with some cynic answer. It's very good to get money, to get grants. But scientifically, we also start to use big data groups. We collaborate with a group from Germany. And what we learned that our data, they are not big data for them. I think if we really want to do it seriously, we need to do open databases, like now already started to do, but they put there not only efficiency and T80, but they put real data. And then sometime these guys from big data, artificial intelligence, can use this data and then maybe have a success. Because my experience with what we now have, we have a European project on it, says that these guys are very unhappy with the limits of our data. And our data is limited because of degradation. And not very a lot of groups, for example, Mark Henkin from HZB, he has now data for 2 years outdoor. Maybe this is, and also he told me that it's not enough. We really need more and more data to use it.
Okay. Thank you, Eugene, for your lecture and very, let's say, nice discussion. And thank you for joining us. Now I would like to, let's think. And now I would like to close this session and remind you